Aerodynamic effects of an engine failure. When an engine failure occurs in a multi-engine aircraft, asymmetric thrust and drag cause the following effects on the aircraft's axis of rotation. A pitch down in the lateral axis, loss of accelerated slipstream over the horizontal stabilizer causes it to produce less negative lift, causing the aircraft to pitch down. To compensate for pitch down effect, additional back pressure is required. The Duchess will experience less pitch down tendency than many light twins. This is because its T-tail design removes the horizontal stabilizer elevator from the accelerated slipstream. You also have a roll towards the failed engine, the longitudinal axis. The wing produces less lift on the side of the failed engine due to the loss of accelerated slipstream. Reduced lift causes a roll towards the failed engine and requires additional aileron deflection into the operating engine. And you have a yaw toward the dead engine, vertical axis. Loss of thrust and increased drag from the windmilling propeller causes the aircraft to yaw towards the failed engine. This requires additional rudder pressure on the side of the operating engine. Dead foot, dead engine. In multi-engine airplanes, the critical engine is the engine whose failure would most adversely affect the performance or handling qualities of the aircraft. While losing any engine is a serious situation, losing the critical engine makes the airplane significantly harder to control, requiring more pilot effort and rudder input to maintain straight and level flight. So why is it critical? On most light twin-engine aircraft, both engines rotate clockwise when viewed from the cockpit. Because of the laws of physics and aerodynamics, the failure of the left engine is usually more detrimental than the failure of the right engine. The four aerodynamic factors that determine which engine is determined critical are remembered by the acronym PAST, P-A-S-T. P factor, asymmetric thrust. At high angles of attack, the descending propeller blade produces more thrust than the ascending blade. This shifts the center of thrust to the right side of each engine. The result? The right engine's thrust is further away from the aircraft's centerline, giving it a longer lever arm. If the left engine fails, the right engine yaws the plane much more violently than the left engine would have. Then you have A, accelerated slipstream. The extra lift created by air moving behind the propeller is also shifted to the right. On the right engine, this lift is further out on the wing, creating a stronger rolling moment. The result? Losing the left engine causes a more significant roll toward the dead engine because of the lopsided lift on the right wing. And then S, spiraling slipstream. The slipstream from the left engine corkscrews and strikes the vertical stabilizer from the left, which actually helps the pilot by counteracting some of the yaw. The slipstream from the right engine spirals away into empty air. The result? If you lose the left engine, you lose that free aerodynamic help on the rudder. T, torque. Since the propellers spin clockwise, the airplane wants to roll counterclockwise or to the left. According to Newton's third law, the result, if the left engine fails, the aircraft is already rolling left towards the dead engine. The torque of the running right engine adds to this roll, making it much harder to keep the wings level. Engine and operative climb performance. Climb performance depends on the excess power needed to overcome drag. When a multi-engine airplane loses an engine, the airplane loses 50% of available power. This power loss results in a loss of approximately 80% of the aircraft's excess power and climb performance. Drag is a major factor relative to the amount of excess power available. An increase in drag, such as the loss of one engine, must be offset by additional power. This additional power is now taken from the excess power, making it unavailable to aid the aircraft in climb. When an engine is lost, maximize thrust, full power, and minimize drag. Flaps and gear up, prop feathered, etc. In order to achieve optimum single-engine climb performance, airspeeds for maximum single-engine performance. VXSC is VX, but on a single engine. Best angle of climb with one engine inoperative. VYSC is VY, but on a single engine. Best rate of climb with one engine inoperative. VYSC will also provide your slowest loss of altitude when experiencing drift down. It is marked in twin aircraft with the blue line speed. In the Duchess, 85 knots is both the VXSC and the VYSC. Side slip versus zero side slip. During flight with one engine inoperative, proper pilot technique is required to maximize aircraft performance. An important technique is to establish a zero side slip condition. Side slip condition is undesirable. When an engine failure occurs, thrust from the operating engine yaws the aircraft. To maintain aircraft heading with the wings level, rudder must be applied toward the operative engine. This rudder force results in a side slip condition by moving the nose of the aircraft in a direction resulting in the misalignment of the fuselage and the relative air. This condition usually allows the pilot to maintain aircraft heading. However, it produces a high drag condition that significantly reduces aircraft performance. Zero side slip condition, best performance. This solution to maintaining aircraft heading and reducing drag to improve performance is a zero side slip condition. When the aircraft is banked into the operating engine, usually 2 degrees to 5 degrees, the bank angle creates a horizontal component of lift. The horizontal component of lift aids in counteracting the turning moment of the operating engine, minimizing the rudder deflection required to align the longitudinal axis of the aircraft to the relative wind. In addition to banking the operating engine, or towards the operating engine, the appropriate amount of rudder required is indicated by the inclinometer ball being split towards the operating engine side. The zero side slip condition aligns the fuselage with the relative wind to minimize drag and must be flown for optimum performance. The single engine service ceiling is a maximum density altitude at which the single engine best rate of climb speed VYSE will produce a 50 feet per minute rate of climb with the critical engine inoperative. The single engine absolute ceiling is a maximum density altitude that an aircraft can attain or maintain with the critical engine inoperative. VYSE and VXSE are equal at this altitude. The aircraft drifts down to this altitude when the engine fails. Critical engine, like we've talked about before, the critical engine is the engine that when it fails will have the most adverse effect on the performance characteristics and handling of the aircraft. The BE76 Duchess, however, is equipped with a counter-rotating propeller on the right engine. This is done so that the failing of either engine will have the same effect on the performance of the aircraft. Therefore, the Duchess does not have a critical engine. You will, however, still be expected to recognize and explain what makes an engine critical in conventional light twin aircraft. On most multi-engine aircraft, both propellers rotate in a clockwise direction from the perspective of the pilot. By coming to understand the following 4 factors, it becomes apparent that in a conventional multi-engine aircraft using 2 clockwise rotating propellers, a failure of the left engine will make the aircraft more difficult to fly and control than a failure of the right engine. The clockwise rotation of the props contributes to the following factors that lead to the left engine being designated critical. P factor, accelerated slipstream, spiraling slipstream, and torque. P factor yaw. Both propellers turn clockwise as viewed from the cockpit. At low airspeeds and high angles of attack, the descending blade produces more thrust than the ascending blade due to its increased angle of attack. Though both propellers produce the same overall thrust, the descending blade on the right engine has a longer arm from the CG or greater leverage than the descending blade on the left engine. The left engine produces thrust closest to the center line. The yaw produced by the loss of the left engine will be greater than the yaw produced by the loss of the right engine, making the left engine critical. Accelerated slipstream, roll, and pitch. Accelerated slipstream causes more thrust to be produced on the right side of the propeller than on the left. This yields a center of lift that is closer to the longitudinal axis of the aircraft on the left engine and further center of lift from the longitudinal axis on the right engine, and it also results in less negative lift on the tail of the aircraft. Therefore, the rolling effect on the aircraft will be greater when the left engine is inoperative than it would be when the right engine is inoperative. The T-tail design of the Duchess, however, as previously mentioned, will greatly reduce the pitch down forces typically associated with this force by removing it from the accelerated slipstream's path. Spiraling slipstream, yaw. A spiraling slipstream from the left engine hits the vertical stabilizer from the left, helping to counteract the yaw produced by the loss of the right engine. However, with a left engine failure, a slipstream from the right engine does not counteract the yaw toward the dead engine because it spirals away from the tail, making the left engine critical. Torque. Every action has an equal and opposite reaction. Since both propellers on a conventional twin spin in a clockwise motion, A reactionary force to this motion will result, feeling like a rolling force in the counterclockwise direction. When the right engine is lost, the plane will roll to the right. However, that right rolling tendency will be reduced by the torque created by the left engine. When the left engine is lost, the airplane will roll to the left, and the torque effect of the right engine will compound to create an even greater left rolling tendency. This compounded force will require greater aileron input to counter, adding drag and making the left engine the critical engine. In summary, on most light multi-engine aircraft, when the critical engine is inoperative, both directional control and performance suffer more than when the non-critical engine is inoperative. VMC is a calibrated airspeed at which, following the sudden critical loss of thrust, it is possible to maintain control of the airplane. For multi-engine airplanes, the pilot must determine VMC for the most critical configurations used in takeoff and landing operations. When the BE76 was originally designed, the historic regulation 14 CFR Part 23.149 outlined the items that would most accurately simulate a critical engine failure and represent the most critical mode of power plant failure expected with respect to controllability. You can use the acronym SMAC-FUM to explain
Standard
this.
day, most unfavorable weight, AFCG, critical engine windmilling, flaps up, gear up to 5-degree bank into the operating engine, maximum power. Any change to the above condition will change VMC, possibly significantly. The following summarizes how VMC may be affected by the above conditions. Standard day sea level. Standard conditions yield high air density that allows the engine to develop maximum power. An increase in altitude or temperature, a decrease in air density will result in reduced engine performance and prop efficiency. This decreases the adverse yaw effect. VMC speed decreases as altitude increases. Most unfavorable weight and center of gravity. The certification test allows up to 5-degree bank into the operating engine. In a given bank, the heavier the aircraft, the greater the horizontal component of lift that adds to the rudder force. As weight increases, the horizontal component of lift increases, which added to the rudder decreases VMC. As the center of gravity moves forward, the moment arm between the rudder and the CG is lengthened, increasing the leverage of the rudder. This increased leverage increases the rudder's effectiveness and results in a lower VMC speed. Critical engine prop windmilling. When the propeller is in a low pitch position, unfeathered, it presents a large area of resistance to the relative wind. This resistance causes the engine to windmill. The windmilling creates a large amount of drag and results in a yawing moment into the dead engine. When the propeller is feathered, the blades are in a high pitch position which aligns them with the relative wind, minimizing drag. A feathered prop will decrease drag and lower VMC. Flaps, takeoff position, landing gear up. When the gear is extended, the gear and the gear doors have a keel effect, reducing the yawing tendency and decreasing the VMC speed. Extended flaps have a stabilizing effect that may reduce the VMC speed. Up to 5-degree bank into the operating engine. When the wings are level, only the rudder is used to stop the yaw produced by the operating engine. Side slip condition. Banking into the operating engine creates a horizontal component of lift which aids the rudder force. With this horizontal component of lift and full rudder deflection, VMC is at the lowest speed. VMC increases with decreasing bank by a factor of approximately 3 knots per degree of bank angle. Maximum power on the operating engine. When the operating engine develops maximum power, adverse yaw is increased toward the inoperative engine. The pilot must overcome this yaw to maintain directional control. Any condition that increases power on the operating engine will increase VMC speed. Any condition that decreases power on the operating engine, such as power reduction by the pilot, an increase in altitude, temperature, low density, or aging engine, will decrease VMC.
A professional pilot is smooth and coordinated.